we now move on to a special topic. Actually, it's a topic which is known to you. We are familiar with electrostatic potential, that is the cross del cross E equal to zero, demands or that gives a reason for the electric field can be represented as negative gradient of a electric potential. So, and we know that electric potential can be assumed to be the or can be simply explained like the energy stored in unit the energy stored from for bringing a charge from infinity to that particular position, or you can say that the potential is actually a function of its position, like any potential energy which specifies due to its state. We say that the electrostatic potential is also the potential or the energy stored for unit charge when it is about to it's brought from infinity to a particular point where an electric field is experienced. Okay, so you can say that that is the way you measure the potential of an electrostatic field. And we know that the electrostatic field, when it goes to time varying one, we have both electric field and magnetic field associated, and then we just modify this E as E equal to minus del V minus dou E by dou T. So we have both electrostatic potential and magnetostatic potential. And what we are going to do here is we are going to explain a charge distribution or a current distribution, and we find if other than what are the different different moments associated with the charge distribution or a current distribution. So we deal with the electrostatic potential first, and then we go for the magnetostatic potential. Okay. So what we do is we know that we have to, in order to find the potential at a position, we have to use a test charge, and we make use of the test charge as small as possible so that the potential of the or the measured the potential that has to be measured is not affected or disturbed by the presence of the test charge. That is already we have explained or studied earlier. Now, what we know that we always measure the force experienced or the energy possessed by a unit positive or a very small test charge when kept in a potential, and that is the way that we measure the potential at a particular point. Now, always we know that V of R can be very easily represented as V of R equal to 1 by 4 pi epsilon 0. You are measuring in the free space. Q by R, that means Q is the source of this potential, and R is the actually position at which it is measured, and you can say that you keep the Q charge at the origin. That is why it comes like you are measuring here at P, and this is R is the position vector. So this is the general and the simplest way of representing the potential at a point due to a point charge kept at the origin, and R is the position vector. Okay, vector R, it is a position vector, and here it is the modulus of the position vector or the length of the position vector from the charge to this. And if you have if you keep this Q in such a way that you have an origin here, and you are measuring the charge or the potential at position R at point P, whose position vector is R, and you are measuring the source is actually kept at another point Q, this is the R dash. So we know that instead of R here, the distance from Q to P is actually R1 same. So you can modify V at R, V at P. V of R is equal to 1 by 4 pi epsilon 0 Q by, here it is R1, and this R1 actually is equal to R1 actually R minus R dash. So you can write R minus R dash. And instead of a point charge, if you have a localized, if you have here it is q, but if you have a localized charge distribution, and if you are measuring the speed, the point P is the point where V is measured, and if you are measuring at a very large distance, which means that you have a distribution here, and compared to the size of the distribution, the distance from the distribution to the point P, the R1 distance, which is already variable, but it is very large. Then we can say that the distribution will look like, you can approximate this distribution to be a point charge, and you can still apply this equation. Okay, and this you can write it as total charge at this is q, and you have a charge distribution v of r equal to 1 by 4 epsilon 0 q by r minus r dash. Same expression comes in simplify, but what happens if total charge q is equal to 0? Will the potential be 0? The equation seems like look like when you have q equal to 0, the potential has to be 0. And if you assume that your mode of r minus r dash is very larger compared to the distribution, very large, then you can say that the v of r actually decreases as 1 by mod r. So for very large r value, even though if you don't have q equal to 0, v of r is going to be like this. Okay, 1 by r. So it is going to be, but what we are just going looking into deeper, like you have a charge distribution and q equal to 0, will the potential be really 0 at a large distance just because q equal to 0? Now why this, you are going to ask why this, because if you have a charge, a physical electric dipole, okay, you consider a dipole, you know that it is equal but opposite charge, separated by a distance, say d. So you have plus q here, you have a minus q here, and they are separated by a distance d, and here you have a point P, which is actually at a very large distance, say r. The d value is very less compared to r, so that the total charge distribution can be taken as a point charge. So here it comes like you have a dipole, and the total charge of the dipole is q plus q minus q. Total charge becomes 0. Still, is the potential at this point v of r, is it equal to 0? Definitely not. We know that there is a potential due to a dipole. So how we can find out is, we just take position, and let this be r minus and let this be r plus. And writing the superposition principle, we know that v at r is actually equal to 1 by 4 pi epsilon 0 q plus q by r plus, okay, plus, actually plus q, here it is minus q by r minus. So this is the total potential at point P. Will it be 0? Definitely not. So this you can write as, this is d by 2, this is also d by 2, this is r, this is r minus, this is r plus. So you can write r plus is uh, actually r minus d by 2, and r minus is r plus d by 2, r plus d by 2. It is r plus is equal to r minus d by 2 is a vector AD. So r plus square is equal to r plus d square by 4 minus 2 r d cos theta by 2. Or you can write it as r plus d square by 4 minus r d cos theta. And r plus you can write it is equal to root of this. Similarly, r minus, if I write r minus is r plus d by 2 implies modulus r plus is equal to r plus d square by 4 plus rt cos theta whole raised to half. Minus half and 1 by r minus is this raised to minus half. So you can write, substituting it here, what you get is v of r equal to 1 by, or you take q by 4 pi epsilon 0, 1 by r plus minus 1 by r minus. And 1 by r plus, as we know, it is r square plus d square by 4 minus r d cos theta 4 plus. So you can write as 1 by r plus or minus is approximately equal to 1 by r plus d square by, r square plus d square by 4 minus or plus. If it is plus, you have to take upper sign, r d cos theta raised to half. Okay, now you can say that this r d square, or you can take it r square, take r square outside, you get this r into 1 plus d square by 4 r square minus d by r cos theta raised to half. And you can see that this part, actually d square by 4 r square, can be neglected. So you can make it approximately equal to 1 by r into 1 minus d by r cos theta whole raised to half. Okay. So substituting it here, no, this is again approximated as 1 by r into 1 minus or plus d cos theta by 2r. Okay, minus or plus, we have one, when it goes to upper, it comes as 1 by r into 1 minus d by r cos theta whole raised to minus half. So it comes like minus, first approximation, 1 minus half into d by r cos theta. So it comes like 1 plus or minus d cos theta by 2r. Okay. So substituting it here, it comes like q by 4 pi epsilon 0. Then 1 by r is common. So take it as common into 1 plus. So 1 by r plus, you have 1 plus d cos theta by 2r minus 1 minus d cos theta by 2r. So 1 and 1 get cancelled, minus of minus becomes positive, and it comes like v of r is equal to q by 4 pi epsilon 0 r into d cos theta. So we take this q d cos theta by 2r. So it is as q d cos theta divided by 4 pi epsilon 0 r square. So even though the total charge is q equal to 0, total charge, net charge by q plus minus q becomes 0. The potential due to the dipole comes as q d cos theta by 4 pi epsilon 0 r square. So you can see that, and you know that qd is the dipole moment of the dipole, and you can write as p cos theta by 4 pi epsilon 0 r square. Okay, now p cos theta again you can write as here cos theta. If you have, you can see that the cos theta is the angle between p and r. So it is the angle between p as well as position vector. So you can write it is equivalent to p of r is actually equivalent to unit vector r dot p. P is the dipole moment, which is directed from positive q to negative q, r by 4 pi epsilon 0 r square. Okay. So you can see here v of r due to a dipole, v dipole is proportional to 1 by r square rather than a point charge. അപ്പോൾ ഇവിടെ ഡൈപോളാർ പൊട്ടൻഷ്യലാണ് നമ്മൾ, ഡൈപോൾ കൊണ്ടുള്ള പൊട്ടൻഷ്യൽ ആണെങ്കിൽ നമുക്കറിയാം ടോട്ടൽ ഒരു പോയിന്റ് ചാർജ് ആയിട്ട് കണക്കാക്കുകയാണെങ്കിൽ ടോട്ടൽ ചാർജ് ഇസ് ഈക്വൽ ടു 0. സോ if you consider it has a total, a single entity, Q is going to be 0 and the potential is going to be 0. Okay? Point charge potential, assuming the point charge, the potential at point P is 0, whereas you take it as a dipole, the dipolar potential, the dipole effect is not 0, but it is lesser 1 by r square. I again consider the case I have a dipole plus q minus q, okay, and separated by distance d. Now I put another dipole which is also separated by distance d. You have minus q plus q, okay. And if I look at a distance at a point P, which is again at a very large distance from the distribution, here you can see that the net Q equal to plus Q minus Q plus Q minus Q is going to be 0. But if I take like this, you have two dipoles, or if I take like this, I have another again identical two dipoles. And if I calculate the potential due to individual ones, yeah, I can do it by the same method. And what will be the potential at this point P. And this two dipoles combined, you get a quadrupole. Okay, and we analyze it, we show that V of R is actually going to be proportional to 1 by R cube. Now, instead of a quadrupole, okay, so what you can see that suppose the dipolar potential, if I take individually, there are two dipoles, and the total dipole in each dipole cancel each other. Suppose even though total Q equal to 0 and the dipolar moment is also equal to 0, maybe you get quadrupole moment non-zero. And if I take two quadrupoles, it's like you have a charge distribution at the corners of a square. Now if I take another square which is at the same distance, and then or you take two quadrupoles and make it an octopole, and again you do the net charge Q equal to 0, but still you have a charge distribution and a potential due to this quadrupole, and V due to octopole will be proportional to 1 by R raised to 4. We will shortly show that or prove it. Okay, so what we know that if you have, instead of a perfect point charge, if you have an arbitrary localized charge distribution, you can say that even though the net charge equal to 0, you are going to have potential due to higher order multipole moments. And we are going to find for any charge distribution, what are the different possible moments. When you consider it is due to the total charge, you call it as a monopole. Okay. Then you have a dipole, quadrupole, octopole, like you can call, they are multipole moments. Okay. Now we are going to find the general case of a charge distribution. It need not be a point charge at all. So what will be the potential due to a charge distribution? Okay, so you're going to consider you have an origin here, and you have a charge distribution distributed over a given volume, say B, and this is your origin, and you're going to measure what is the potential due to this charge distribution at point P, which is at the position R. This is your R, and this is R1, and it is a point. So you have to consider, you're going to find the potential due to this charge distribution over a volume V, which is distributed at a distance, say R1 from origin, at the position R1 from origin, and you're going to find what will be the potential at this point P, which is having a position vector R. Okay. So this R1 is subjected to change because it is a distribution. Now you consider a very small volume V tau at a position R1, say R, it's again R1, so just change it as R dash. Okay, so this is R dash, and you have a volume charge distribution rho at R dash. Okay, and the total Q can be written as rho V tau, rho at R dash, dτ. Okay, so we can write potential at position R is actually 1 by 4 pi epsilon 0 integral over rho of R dash dτ divided by it is R1, because R dash, this point, this small volume element, infinitesimally small volume element, lies at the position R dash, and that is having a with respect to P, it is at the distance R1. Okay, so this is R dash, this is R, and this is R1. So the charge distribution and the position or in the R1. Now we have to evaluate this for an arbitrarily charged distribution at a position R dash. And we know that you can write R1 is actually equal to R minus R dash, or mod R1. Mod R1 is equal to R1 square is R square plus R dash square minus 2R R dash cos theta, where this is angle theta. Or you can write, you take R square outside, you get as 1 plus R dash by R whole square minus 2R dash by R cos theta. Okay. Now you can write as R1 as here it is R1. R1 equal to root of this means R into 1 plus R dash by R whole square minus 2R dash by R cos theta whole raised to half. Okay. So R is actually the position or the distance at which P is present. So that is something fixed. It doesn't come inside this one. Okay. So we can say that V of R is actually equal to 1 by 4 pi epsilon 0. Then 1 by R is this one integral over the volume. Actually, it is this volume. Rho of R dash dτ divided by this one. Okay. Now divided by R1 is 1 by R into this. So 1 by R1 you can write as 1 by R into 1 by this, which you can write as 1 plus R dash by R whole square minus 2 into R dash by R cos theta whole raised to minus half. Okay. So you can write as rho of R dash in dτ into 1 plus R dash by R whole square minus 2R dash by R into cos theta the whole raised to minus half. Okay, you can take this dτ from dτ. And dτ is actually the volume element. Maybe here it is spherical polar coordinate system. You can write it as dτ becomes R square sin theta d theta d phi. Okay, with the given extension of R, theta, and phi. For any type of charge distribution, you can assume it. Now, our case is, if you know rho of R dash, you have to evaluate this with this function 1 plus R dash by R whole square minus 2R dash by R cos theta whole raised to minus half. Okay. Now, take a closer look at this function. R dash by R is equal to say t, which is a familiar expression. That's why you can put it as x, y, z, whatever. I'm just taking R dash by R equal to t. And we know that the R dash is very, very less than R, which means that t is very, very less than 1. Why? Because R dash is corresponding to the charge distribution. Okay. And it actually need not be so. Still, I assume that R dash is less than 1. So R dash by R equal to t. And I put cos theta dash is equal to x. Soon as this function becomes 1 plus t square minus 2tx whole raised to minus half. And this one is very much familiar to us. We know that this is g of xt, generating function for p n x, the legend of polynomials. So we know that g of xt 1 minus 2xt plus t square whole raised to minus half is the generating function such that it gives you sum over n equals 0 to infinity Pn of x t raised to n. So this way we can write this is actually a summation extended from 0 to infinity or infinite series of Pn x and t. Here it is r dash by r. So that means you can write V of r as a sub infinite series as 1 by 4 pi epsilon 0, 1 by r integral over, now you have to put this function as sum over n equals 0 to infinity Pnx. Now Px is cos theta dash and t raised to n is r dash by r whole raised to n rho of r dash d tau. Okay. So what happens is you have integral over different terms. Or you can write, in conversely, you can write as V of r is actually equal to 1 by 4 pi epsilon 0. Now 1 by r is common. Then you take sum over n equals 0 to infinity integral over Pn cos theta dash r dash by r whole raised to n rho of r dash d tau dash or d tau. Okay, so you have an infinite series, and if you put n equal to 0, what you will get is, so you can just expand some of the expressions for epsilon 0. Now you have to take n equal to 0, integral, first term is integral p0 cos theta dash r dash by r whole raised to 0, I have 1 by r here, so 1 by r I take here, rho of r dash d tau plus, this is the first term, plus, take it out, 1 by r integral p1 of cos theta dash r dash by r whole raised to 1 rho of r dash d tau dash, second term, plus 1 by r integral p2 cos theta dash r dash by r square rho of r dash d tau dash plus and so on. Now if I take the first term, what you get is 1 by 4 pi epsilon 0 p0 cos theta, p0 is 1. Now you have this is 1, you get this 1 by r integral rho of r dash d tau. Now what is this? This is the total Q. So you can write it as Q to the monopole or the total charge. You have taken it as a total charge as a single point charge. So it is rho r dash d tau is actually gives you the total charge. Okay, so it comes as 1 by 4 pi epsilon 0 Q by r. You can say that it corresponds to the monopole. Okay, now if you take the second term here, you get it as 1 by 4 pi epsilon 0 1 by r integral. You can say that p1 cos theta is actually cos theta dash r dash by r rho of r dash d tau dash. Now this r is you can take outside. Now you have to evaluate this as rho r dash cos theta dash d tau dash. Okay, so depending on the nature of rho of r dash, you will get this an expression in the total value, and you can see that the potential is proportional to r square, okay? And this corresponds to n equal to 1 in the expansion, and you can say that this potential actually gives the dipolar contribution to the potential. So naturally this term, the third term, will be giving you quadruple contribution. If you take the next one, you will get the octuple contribution. So here we have not given any kind of approximation. We have taken all the terms here and you will have an infinite series. And if you can see that even though total charge Q becomes 0, there will be the second term can be non-zero. It's made with the highest terms. If Q is not 0, this term will be predominant. Okay. So you always the lowest non-zero term is approximated for the potential at that particular point, and but for larger values. But if you need a greater precision, you always can take second term, third term, and higher terms with it for a better or improved result. Say. Okay. Now you can say that we have what we have taken as the generative function expression. You can actually expand this. Actually, by you can go for the binomial expansion of root of 1 minus r dash by r whole square, 1 plus r dash by r whole square minus 2 into r dash by r into cos theta. You can take the binomial expansion of 1 plus x raised to minus half, and you can take the coefficients, and then you will see that they corresponds to the Rodriguez formula for Pn of x. But I find this as the best, or this is the easiest one, because we are familiar with the generating function of Legendre polynomials. Okay, so but even though if you are more okay with the Rodriguez formula, you can use that, and still you will get the same expression. And what you have to do, say P2 cos theta is actually 3 cos square theta minus 1 whole divided by 2. Okay, so you can evaluate this. So I'll give you an assignment for this. What you have to do is a sphere of radius is given in your text as, so a sphere of radius r and center at origin have a charge density of r theta equal to a constant into r divided by r square into r minus 2r sin theta. So this is the way actually the potential is being distributed. So you can say that sin theta is something like theta distribution over theta. And what we have k constant, and r and theta are the spherical polar coordinates. Okay, so find the approximate potential for a point on the z-axis, and you take the point far from the origin. So you have to find, what you have to find is approximate potential only. So you have to find V monopole, V dipole, and if V monopole is non-zero, you can write that as the approximate expression. If this is zero, you go for V dipole and find it. If that is also zero, you have to go for V quadrupole. Okay, and if that is zero, you have to go for the V octopole. Okay, so always find an integral, and here you have to see rho of r theta is given. In our expression, we have taken as rho of r dash. Okay, so you have to you have to do r dash theta dash. So you put it r dash sin theta dash, and this r is actually the radius of one. And for r, actual r, you have to put you have to measure it along the z-axis. So instead of r, you can put it as equal to z from the charge distribution. So actually, this is a sphere of radius r, and you can say this is r, but the charge distribution is not spherical. So please do work out this and work for any